Okay, so simple function transformations. Let's have a look. I want to make this a little bigger though. How about if we do that? Okay, so if I have a function and I want to tweak it. Okay, I want to transform this function we're going to start off with pretty simple ones, and later on we'll get into some more complex ones. If I want to, for example, this is my function f of x, and I want to slide it left, what do I do? Okay, so I'm going to subtract something from x inside the function, right? So if I want to do a horizontal translation, I can do something like this. So if the red one is f of x, right, the new one, I guess that's kind of pink, in this case would be k of x, we're calling it. K of x equals f of x plus 1.9. And look what that did. It slid it to the left by 1.9 because I'm subtracting a negative to get a plus sign there, aren't I?
Yeah.
Right?
Yeah.
Now if I slide, I wonder if I can do this. I bet I can do this up here. Hang on, I gotta do one thing though. Yeah, I can. You know what, okay. This is gonna be hard to see a little bit, but I have to unzoom it for this to work.
Why don't you just move that thing?
Okay, now let's try it. Look, if I see what's going on?
No.
I need attention up here, please. Okay, let's do this real quick. We need this. Okay. If I drag the value of c, all I'm doing here is I'm changing the value of what's being subtracted from x, right? So if I subtract big values, like f of x minus 3.5, all I've done is slide the whole thing to the left by 3.5, right?
You're sliding to the right.
I mean to the right, sorry, I got the backwards.
If you subtract it
If I
to the right.
subtract, right, exactly. If I subtract positive values, I'm sliding it to the left.
What is that?
What?
Whoa.
Okay, well, yeah, now, and what's confusing about that is, it seems like that'd be positives, right?
Yeah.
But think about this. If I'm gonna put in a value of, let's say, all the function c's, I'm gonna make this a little bigger so you can see what's going on. So the red function is just f of x. Our new function, k of x, if that's f of x minus 3.5. Okay, now think about this. The function is like a machine, and you're inputting numbers, input values, x values, and it's outputting y values. It doesn't care a bit where those numbers are coming from. It's just getting the numbers, processing them, and spitting them out, right? Now, the function that we're using here, this f of x function, has this weird shape. And who knows what the formula is for that? We're not concerned with that at this point. But it knows that if I feed it a 0, for example, it's going to have a y value of 0. Okay? Now, if I want the function to be seeing a y value of 0 instead, when I feed it a value of 3.5, how am I going to accomplish that? Okay. It has to be a minus sign, doesn't it? Right? Because x is the value that I'm feeding it, right? If I want the function to see the overall value, that's all it cares about. Doesn't matter where it's coming from. If I want it to see the number 0 instead of the number 3.5, don't I have to subtract 3.5 from all the input values? You see how that works? Well, if my goal is to slide the whole thing to the right by 3.5, we know that the red function, f of x, when I feed it a value of 0, it knows that it's gonna make that point right there. So it's gotta, would you agree that the coordinates of that point are 0, 0, right? So if I wanna take the same shape of the graph, but just slide it to the right by 3.5, I'm gonna call that k of x. Well, k of x is gonna be f of what? I'm gonna be feeding, I still wanna be feeding when I input a 3.5 for x, right? Because the coordinates of this point right here are just 3.50, right? I want f of x to think it's getting a 0, right? Because when I input a 0 into f of x, it's gonna spit back a y value of 0. I just wanna take this particular point and scoot it over here, right? With my new function k. So to trick f of x, and that's kind of a way of thinking about it, into thinking to produce a y value of 0 because it thinks it's getting an x value of 0, I would just subtract 3.5 from all of the inputs, right? Does that make sense? Because f is what's determining the shape. The shape of this thing is that, right? Okay, so when I input a value then of 3.5, if I actually subtract 3.5 from that before I feed it to f, it thinks it's getting that input value of 0. Does that make sense? Yeah, it takes some thought. I mean, it's not just a simple concept. I guarantee if you think about this a little bit, you're going to get to the point where you're going to go, oh, okay, I got it. It makes sense, right? So when we want to slide something, we have to, if we want to slide something to the right, we effectively are just having to subtract from the x values that we're inputting into the original function, that amount that we're sliding it to the right, okay? Because when I input 3.5 for x, I want to be feeding this red shape a value of 0, right?
Right.
Make sense? Because I don't want it to be at 0 anymore. I want that vertex to be at 3.5, okay? So that's why it's odd, but that's why we have that negative sign there. In fact, that's a general case. That's always going to be the way it is for any function. Not this one, it's anything, right? If I wanted to slide left, well then the opposite would be the case, right? If I wanted this thing to slide left, I want to be inputting a negative value, right? And having the red shape think it's getting 0. So if I were to input negative 3.5, right, that'd have to be a plus sign then, wouldn't it?
Yeah.
Because if I input negative 3.5, I would have to add a positive 3.5 to feed the red shape that 0 for x. So it knows to spit out the red y value of 0 for the vertex. Okay? You have to sit there and ponder that a little bit before it becomes clear, but it will. I'm going to put this thing, I'm going to put a link to this on when you go to the Moodle page for Unit 1, at the top, there's the resources. You probably only use the PowerPoints at this point. I don't think there's any links in there. I can't remember if there are. But I will put a link to this in the important links part, and I've actually got a handout I'm going to give you too. That I won't give it to you, I'll just put it in the folder, put it in Moodle, and you can print it if you want to. But it's going to have just a little cheat sheet that talks about the different transformations. Okay? And for now, practically speaking, if you want to just be able to manipulate functions and move them around, and I don't think this is the way to do it in general, but really, you just got to kind of almost remember that when you subtract a number from x inside the parentheses, what that's doing, the number you're inputting there that you're subtracting from x is how far you want to slide it right. So if I make this number that's being subtracted from x positive 3.5, I'm sliding it to the right by 3.5. Right, because I'm subtracting the number 3.5 from x, and remember what that number means. How far is it sliding to the right? If I want to slide it left, well that's just, I got to make it negative, because left is just negative right, isn't it? Right, if I want to slide it to the right by negative 3.5, aka the left, it'd be x minus negative 3.5, which would make that a plus, which would look, of course, like this. I doubt I can get it that accurate, but we'll try. Well, I can only get it up to 3.3, but you see what it did? Okay.
Yeah.
All right, so that's sliding it horizontally, okay? Now what about sliding it vertically. That one's a little easier maybe to see. Come on. Come on, what are you doing? Why is that? There we go. Okay, if I want to slide it vertically, what do I do? If I want to slide it vertically up. Okay, good. I'm just going to add a constant to the whole thing, right?
Yeah.
Okay. Like that. Whoops, not that. Sorry. Like that. That. There we go. Okay, so now I've just added to my function positive 3.3. Hey, don't talk. I've just added to my function positive 3.3, and what that did is it took every one of those infinite red points and it shifted them up by 3.3, right?
Yeah.
And that makes sense. That's what we're telling the function to do. We're just saying take the original red function plus, for every value of x we input, let's also add 3.3 to it, right? To move it down, obviously, what do? Yeah, I'm just going to add a negative, which is the same as subtracting, right? So we can just do that. Okay, so what if I want to stretch this thing vertically? Then what do you suppose I'm going to do? I'm going to multiply it. Okay, I'm going to multiply the whole thing by some coefficient, okay, by some number. Now, if I want to stretch it, that number has to be, give me an example of a number that would stretch it vertically.
7.
Okay, if I multiply the whole thing by 7, that's going to work. Then what's that saying? That's saying that the original function, the original red function, for every x value I input, I get the original y value times 7. So it's going to move it up, not that far, but 7 times as high. It's going to stretch it up vertically, right?
Couldn't you do 80 number?
I could. 7 would work. What's another one that would work?
80.
Sure. Well, not any number. Not any number. Say it again. Well, infinity's not a number, so that's not going to work. Yeah.
Any real number.
Okay, now we're getting closer. Any real number, but can you think of a real number that's not going to stretch it vertically? Give me a counter example.
The absolute value of less than 1.
Okay, so yeah, if the absolute value of the number is less than 1, for example, what if I put in like 1/2? Is that going to stretch it vertically? No, that's going to shrink it because now the original y values are being multiplied by 1/2, so they're going to get compressed. So if we wanted to say all the numbers, somebody come up with, here's a little more of a challenge. Come up with, how would you describe the set of all numbers that would stretch it vertically? Okay, any positive number greater than 1, right? So I mean that would be, I guess that would, if they're greater than 1, they're all positive, right? Let's take an example. Look what happens.
Is that a sneeze or
I would be.
okay?
Okay, so there's 2.6. Everybody look, please. 2.6. There's 3.1. It's getting bigger.
But like
1.6. What happens when it gets to 1? It's going to be the same. If I multiply something by 1, it's just exactly the same, isn't it? They overlap. That didn't do anything, right?
But the bottom point stays the same.
Everything would be the, oh yeah, it would, because 0 times what is, 0 times any number is what? 0,
Okay.
right? Okay.
So like all these functions have to be on the vertex.
Say it again.
Do all the like anything that we're gonna like move or stretch, it doesn't have to be on the vertex.
No, it wouldn't have to be. What would happen, here, let's do this. Here, let's do, where's Kaylee sitting? I saw Kaylee up there. Did I not see Kaylee?
She's right there.
Oh, there she is. I knew I'd seen her. Okay, good question. So let's, before we vertically scale this thing, let's go ahead and vertically translate it, right? So what if I do both? Well, I'm going to take this, now we're going to take the blue function, which has been picked up a little bit, and we're going to scale that vertically. Okay, so now if I scale this one vertically, when I scaled the red one, that point was kind of stuck in place.
Yeah.
Are any of those points going to be in the same place when I scale it? No, they're all going to get moved, aren't they? Right? If this one was originally a distance of 1 away, this vertex now, instead of being on the origin, when I scale it by a factor of 2 vertically, it's going to, instead of being there, it's going to be there, isn't it? Right? Yeah, I'm sorry, I got to answer this, Mike.
Is this what we have? Is this what
Okay,
the
so here we go. All right, back with me. All right, so now if we take this blue one and we scale it, watch what happens. We vertically scale this one. This is good stuff. And I'll let you play with this when we get down there. In fact, I'd rather have you be playing with this than me playing with this, so I'll make this quick and then you can go mess with it. But now watch what happens.
Oh, what the heck?
See, look what's happening to the blue one.
Wait, what? Why did
Oh,
they
you
have
know what?
that?
No, that didn't work, did
Yeah,
it?
that didn't work.
Whoops, didn't work. Can't do both, sorry. Thought I could, but it won't, it's not as smart as I thought. Just do all.
Do them all now.
It looks cool.
It did look cool. Okay, so how do I make the thing, let me ask you this. How could I flip it?
Roll reflection.
Okay, so if I want to reflect this, over the x-axis, what would I have to do to f of x?
Times by negative.
Multiply by -1, sure, right? Makes sense, doesn't it? Now think about that. Think about that in terms of what we're doing to the function. As we input a value of x, and the red function is spitting out a y value, we just want to make that the opposite y value. So we multiply by -1, right?
The whole thing are just in little parentheses.
This is present.
Okay, I'm going to ask you guys one more time. Clearly, we're going to have to do some different kinds of seating arrangements here. I did not see that one coming in an Honors Algebra 2 class, but it's going to have to happen, I think. Okay, let's try this one more time. Yeah, I'm up here, you're out there, let's get it fixed. All right, so multiply by -1 to reflect it. Now, yes?
Do you multiply it in the parentheses? or
No,
all
just
of
the
it?
whole thing.
Okay.
The whole thing, because you want the red f of x function to calculate its value first, right? And then you're going to multiply that value by -1. Okay, so here's an example. Let's say we had the function, the original function was, did it work?
Yeah.
All right. Let's say the original function was something like the square root of x plus 1. Okay, so there's the formula that's calculating the y values for each x value, right? Now, if I want to flip that, if I want to create a new function g of x that's going to flip that whole thing over the x-axis, what is g of x going to have to look like?
X squared minus 1.
Okay, no, now you're thinking about doing you're getting more complicated. You're doing inverses or something like that. We just want to flip it.
Oh.
So negative, okay, I'm going to need parentheses, aren't I? Because it's this whole thing being multiplied by -1, right? So it's really negative the quantity square root of x plus 1. Now if we simplify that and distribute, we just get, well that's bad negative sign. We just get negative root x minus 1 in this case. Yes, ma'am?
So if you don't know what f of x is, then you can't reflect it?
Well,
Or can you?
okay, I mean, I see what you're getting at, in a sense, but couldn't I also just do this then? Couldn't I just say g of x equals negative f of x?
Yeah, that's what I was wondering.
Yeah. Right, it means the same thing, but if we put in the specifics, it looks like that for that particular
Okay.
function, right? So what if I wanted to reflect it over the x-axis and shrink it? What would I multiply by? Instead of -1, I would multiply by, give me an example.
Negative 0.5.
Say it again.
Negative 2.
-2, I want to shrink it though, not stretch it.
Oh, negative 5.
Okay, -0.9, -0.5, -0.3. A negative number whose absolute value is less than 1, right? Make sense? So between 0 and 1. What if I want to flip it over the x-axis and stretch it? Now there's my example of -2 or -10 or -1,000,000 or something, right? Okay, last issue for now. What if I want to take this original function and I want to reflect it over the y-axis? That's a little trickier.
You just put the x.
You multiply.
This one's
the
good.
Negative and like the f of x.
Okay, yeah. Now think what you want to accomplish. You want the red shape, the original red function, to be seeing x values that are opposites, right?
Yeah.
You want it to think, when you're feeding it a value of +1, you want it to think it's getting a value of, or when you feed it a value of -1, sorry, you want it to give you back the y value of the original function, right? So you want the red shape to be seeing a value of +1 when you're actually giving it -1. So when you're there, you want to get that same y value you had originally at +1, right?
Yeah.
Okay, and so the way you're going to trick the function this time is just by multiplying all the inputs by -1. Okay, so let's look at that one, right? So if I put in a value of -1, notice that's an exact, I've taken the red one and I have reflected it exactly over the y-axis, right?
Yeah.
Okay, and that's just f of -x. Okay, so I got an example. Okay, back table in the corner, you guys are on the spot, you're talking. I want to know if this is my original function, if f of x, we'll go back to square root of x plus 1. If I want to create, g of x, that is going to reflect it over the y-axis, what's it going to look like? No, going back up. You guys are on the spot. What are you going to do?
Square root of -x plus 1.
Good. Square root of -x. And then outside give you the +1, right? So effectively, when you're thinking about that in terms of how do you do that algebraically, all you're going to do is you're going to make the substitution where you used to have an x, you're going to substitute the quantity -x
To flip it over the exact
to flip it over the y-axis,
Exactly.
right? To flip it.
Oh, so then it goes, because you're on the X line, you're just changing
Right,
this
right.
half, but it's on the X line. Oh,
Okay, so I got a tricky last one, and then we'll get you out of here. Look at this. Here's my double dog dare you to figure this one out. Okay, so if my original function is x squared, let's say I want to reflect the function, the parabola x squared, over the y-axis. Okay, x squared, remember, looks like. Can you tell me? You guys tell me what does x squared look like? Okay, yeah, it's a u, right, with the vertex 0, 0 at the origin. Okay, so here's my. There's f of x.
Wait, would it look any different if we flipped it?
Would it look any different? It's going to look the same.
Yeah.
It's going to look exactly the same when I reflect it, isn't it?
But what's the y?
Okay, but now if that's the case, and this is where I think this is where math starts to get really interesting, is that if that's the case, what does that imply about the algebra? If I make that substitution, if the graphs look identical, if I make the substitution that flips it over the y-axis, should the function look any different? Should it? If they overlap exactly, if their graphs are the same, doesn't that mean the functions are identical? So how's that going to work? Now, doesn't that seem weird that I'm gonna make that trade? I'm gonna trade -x for x, right? Swap where you used to have x's.
So then you want to do something else, then it'll be different.
Okay, but if we do the algebra, if we simplify this, wouldn't you agree that conceptually, if you think about this kind of philosophically, it's got to look the same because the graphs are the same? Well, it will. Let's look. So if I take g of x equals, all I'm doing is taking the -x, taking the x and replacing it with a -x. If I square that, okay, now what is the quantity -x squared? Yeah. If I square a negative, isn't it positive?
Yeah.
Right? That's really like saying -1 squared times x squared.
So it is.
So it is exactly the same as it had to be because the graphs overlap, right? Okay?
Yeah.
Now, we'll talk later more about this. That's what we call an even function. If there's a function that is insensitive to flipping it over the y-axis, in other words, if it's got line symmetry on the y-axis, that kind of thing will always happen. Okay? Let's get out of here, though. Let's go down to 205 and let you work on this stuff.
I got you.